this is part 2 of the compiler overview. We completed part 1 last time. First of all, we will have a quick overview of what we did last time and then continue with the second part. So, last time we looked at the block diagram of a compiler. So, this is what we saw. There is a lexical analyzer phase which changes the character stream into a token stream. There is a syntax analyzer phase which changes the set of tokens according to a programming language grammar to a syntax tree, and the semantic analyzer changes syntax tree into an annotated syntax tree in which it checks all the semantics of the programming language. Today, we are going to look at an overview of the intermediate code generator, the machine dependent code optimizer, the code generator, machine independent code optimizer, etc., etc. So, this is the slide I showed you last time regarding lexical analysis. The input is an assignment statement Fahrenheit equal to centigrade into 1.8 plus 32 and a sequence of tokens id comma 1 assign, id comma 2 multop, fconst comma 1.8 addop, iconst comma 32 comes out of it. This goes into the syntax analyzer and the syntax analyzer parses this particular sequence of tokens and produces the assignment expression tree as shown here. So, the next phase is the semantic analysis phase in which the syntax tree is validated. For example, the constant 32 is changed into a floating point constant using the function into float which is inserted into the tree. Similarly, there are checks made whether ID and ID 1 and ID 2 etc., are all compatible with the assignment operation and so on, and finally, it goes into the intermediate code generation. This is the intermediate code generation overview. So, the semantically validated expression tree or the program tree is the input to the intermediate code generator. The output of the intermediate code generator looks as shown here. For example, the bigger expression is broken into smaller expressions, T 1 equal to ID 2 into 1.8 is a small expression, then T 2 equal to into float 32 is another assignment statement, T 3 equal to T 1 plus T 2 and finally, ID 1 equal to T 3. So, now let us see why all this needs to be done in the compiler. While generating machine code directly from the source code is definitely possible, it is not an impossible problem, but when we do so, we lose out on many things. There are two problems that are well known. For example, if there are m languages and n target machines and we generate compilers directly, rather we write compilers directly, we generate machine code from the source language, then we need to write m into n compilers. Hardly any part of the compiler can be reused, and there is a lot of effort in writing a fresh compiler. The first part of a compiler can always be reused, that is the lexical analysis, the syntax analysis and the semantic analysis can always be reused whether we are generating intermediate code or we are generating machine code. But if we are generating machine code directly, then the code optimizer, which is one of the largest and most difficult components of any compiler, cannot be reused. So, what happens is the code optimizer will have to be now targeted towards the machine code which is being generated, and therefore, every machine code has its characteristics which are very different from each other, and we will not be able to reuse this particular code optimizer. Whereas, if we convert source code to an intermediate code, a machine independent code optimizer may be written. So, what is this intermediate code? The intermediate code is some sort of a universal assembly language. Of course, it should be easy to produce, it cannot be as difficult as machine code to produce, and it must be easy to translate it from intermediate code, any intermediate code to machine code as well. And another important characteristic is that it should not contain any machine specific parameters such as registers, addresses, etc., etc. The reason is if it contains machine specific parameters, the machine independent nature of the code is lost. So, we will again be back to square one, and we need to write the machine code generator and this even the optimizer, etc., all over again. So, this independent machine independent code is usually produced during a traversal of the semantically validated tree. There are different types of intermediate code. It is not that the same intermediate code can be deployed in every application. So, it depends on what type of application we have in mind when we design the intermediate code. For example, quadruples, triples, indirect triples, abstract syntax trees, these are some of the classical forms of intermediate code which are machine independent, and then these can be used for machine independent optimization and also for machine code generation. That is fairly easy. These are very well known and they are used in almost every compiler. There are two other special forms of intermediate code that I am going to mention here. One of them is the static single assignment form called SSA. This is a very recent intermediate form, and this is much better than the other type of intermediate code that is used in compilers. So, because we can do many more optimizations more effectively on this particular static single assignment form. We are going to look at the details of SSA in one of the later lectures. For example, conditional constant propagation and what is known as global value numbering are two optimizations which are far more effective on the SSA form than on any other form. The other special intermediate code that I mentioned here is the program dependence graph, PDG as it is called. This is very useful in automatic parallelization, instruction scheduling and also software pipelining. Here is an example of translation to produce quadruples from arithmetic expressions. So, let us go through it step by step. The grammar is a very simple grammar. S going to ID equal to E is the production for assignment. S E going to E1 plus E2 is the sum expression. E going to E1 star E2 is the multiplication expression. E going to minus E1 is the negation. Then E going to bracket E1 bracket is the parenthesized expression. E going to ID is the terminating production, which gives you a single variable. So, if this is the grammar, first of all let us look at the kind of expressions that we produce and then come back to this grammar all over again. Here is a nice example. Let us say we have a simple tree in which A equal to B star C plus D is the expression, right. So, B star C plus D is the expression and it is being assigned to A. So, this is our complete assignment statement, and now let us go back one step and see how this is translated. Before that, please observe the syntax tree that is produced. So, at the first level we have ID, then equal to and E. At the second level we have E plus E, and at the third level we have E star E, and at the fourth level we have the identifiers, right. So, the code generation, the intermediate code generation actually goes in a bottom up fashion. So, for example, the code is generated for E going to E star E first, and then the code intermediate code is generated for E going to E plus E, and finally, the intermediate code for S going to ID equal to E. So, let us see how this happens. So, if it is an assignment ID equal to E, we search, the action indicates that we search the symbol table, get the pointer for that particular name from the symbol table, and if the name is already present in the symbol table, then the pointer is not null. Then we generate just the simple assignment statement in the intermediate code ID PTR equal to E dot result. So, E dot result is the place where the result of the arithmetic expression is going to be placed. This E dot result is also a pointer into the symbol table. It is not that it is a machine location. The machine location will come later and it will be assigned during the machine code generation phase. So, if the name is not present in the symbol table, obviously it is an error. Let us take the next production, E going to E 1 plus E 2. So, in this case we have the result of E 1 in E 1 dot result, the result of E 2 in E 2 dot result, and to add them up we actually need a temporary. So, the gen temp routine creates a temporary, and E dot result equal to gen temp will transfer the pointer into to the temporary variable into the variable E dot result. So, gen temp actually generates a temporary name and puts it in the symbol table and also returns a pointer to it. That is the way we have assumed it. So, now once the temporary is generated, the next is to generate intermediate code E dot result equal to E 1 dot result plus E 2 dot result. So, there we have the intermediate code for the arithmetic expression consisting of plus. E 1 star E going to E 1 star E 2 is very similar, instead of plus there is a star, otherwise there is no difference. Similar is the case of E going to minus E 1, and E going to parenthesis E 1 parenthesis does not require any intermediate code generation. It is just that the location where the result of E 1 is stored is transferred to the location E dot result. Finally, E going to ID again makes us search the symbol table, get the pointer to the name ID dot name, and if it is not null, then the place E dot result is going to be the pointer to the symbol table, otherwise it is an error. So, in other words, there is no code generated for the productions 5 and 6, it is only for the other productions that we have really generated the intermediate code. Intermediate code is very similar to the higher level programming language code, but the most important characteristic is that it can have only a single unary operator or a single binary operator. Bigger arithmetic expressions have to be broken into smaller ones, and finally temporaries must be used to calculate the result. So, this is very clear from this particular diagram. So, if you look at this expression E going to E star E, E dot result is B for this particular E dot result is C for this particular E, and here we generate a new temporary T 1 and E dot result will be T 1. Here E dot result is D, here we generate a new temporary T 2 and that will keep the result of T 1 plus D, and finally, the assignment is A equal to T 2. So, the intermediate code that we generate would be T 1 equal to B star C, then T 2 equal to T 1 plus D, and finally, A equal to T 2. So, these are the 3 intermediate code statements that would be generated in a bottom up fashion. Now, let us look at the next phase of compilation called the code optimization. This is the input that we got from the output that we generated from the intermediate code generator. Here we have these statements, but as you can see there is some inefficiency in these. Look at the output here. the output that we generate after the code is optimized. It directly says T1 equal to ID2 into 1.8 instead of accumulating ID2 into 1.8 in T1 and then T2 equal to into float 32 and then T3 equal to T1 plus T2 is directly and then ID1 equal to T3 is directly translated into ID1 equal to T1 plus 32.0. So, the three statements T2 equal to, T3 equal to and ID1 equal to have been combined into a single statement ID1 equal to T1 plus 32.0. So, such elimination of unnecessary statements is possible using the code optimizer. Code optimizer improves the quality of the intermediate code that is generated and feeds it into the code generator. So, here is the detail. Intermediate code generation process introduces many inefficiencies. This is the reason why we require the code optimizer phase, machine independent code optimizer phase. So, extra copies of variables, that is the temporaries, we already saw that T1, T2 etc. are all temporaries being generated, and then using variables instead of constants. So, we would have simply initialized the variable to a constant and use that variable in place of the constant, and then there are expressions which are going to be repeatedly evaluated. So, these are all the sources of inefficiency. We can eliminate these. If there are extra copies of variables, we can retain one of them and eliminate the rest. Instead of variables, we can simply do constant propagation and replace the variable name by the constant value. And in the case of repeated evaluation of expressions, we evaluate the expression only once and use the same value again and again. So, code optimization removes such inefficiencies and improves code, that is what I just now mentioned. Improvement may be time, space or power consumption. For example, we may want to make the code fastest. So, in that case we want to minimize the amount of time that the code takes. We want to make the code space efficient. For embedded applications, the amount of memory that the code takes may be very important, and in such case the number of instructions will have to be reduced in order to save space. Finally, in the same embedded applications such as sensor networks, power consumption is a very important factor. So, we may want to actually optimize the code to save power instead of time or space. So, it is possible to do optimization in many ways. The code optimizer also changes the structure of programs. Sometimes it is beyond recognition. So, for example, the functions are all inline, there are no functions anymore, the body replaces that function call. Unrolls loops. So, if the loop runs from 1 to 10, 1 to 1 million, maybe I am going to unroll the loop 1000 times and run the loop only from 1 to 1000. The rest of it is unrolled and it is going to be a huge body inside the loop. And it also eliminates some of the programmer defined variables etc., etc. For example, if the same variable, the different variables have the same value, as I told you, we can use one of them and eliminate the rest. Code optimization consists of a bunch of heuristics, and percentage of improvement depends on the programs. Well, you see, this is a heuristic. So, it is not guaranteed to give you any definite result. If the improvement happens, then it is very good. If the improvement does not happen, even then it is not going to change the functionality of the code. That is the best guarantee that can give you, but on the average most of the programs benefit by code optimization. Then here are some of the examples of machine independent optimizations. Some of them I already mentioned. For example, common sub expression elimination, the same expression need not be evaluated again and again. Copy propagation. So, I do not have several variables carry the same value. So, I do not have to keep all of them, I can just use one of them. Loop invariant code motion. There is a lot of code inside a loop which is not altered inside, then in that case the code can be moved outside the loop. partial redundancy elimination is a bit complex to explain, but it is one of the most useful optimizations, and we will be looking at it in detail in one of the later lectures. Induction variable elimination and strength reduction are similar. They actually are carried out in a loop. So, multiplications can be changed to addition, and induction variables, which are nothing but incrementing variables, sometimes can be eliminated. Code optimization needs information about the program, this is very obvious, and the compiler actually obtains this information using a process called Dataflow Analysis. So, for example, which expressions are recomputed in a function, which definitions reach a point, these are some of the optimizations possible, the informations that are necessary for an optimization. Next, the code generation process is it follows the code optimization process. For example, the intermediate code which is improved in a code optimizer is input to the machine code generator, and here is a sample of the machine code. The assignment statement T1 equal to ID2 star 1.8 is translated into load floating point R2 comma ID2 and then multiply floating point R2 comma 1.8. So, now R2 will contain the value of the expression ID2 star 1.8, and now instead of ID1 equal to T1 plus 32.0, since the value of T1 is already in the register R2, we can simply say add floating point R2 comma 32.0, and finally store floating point ID1 comma R2 will assign the value of this entire expression to ID1. This is the sample machine code which is generated in a compiler. So, here is some detail. A machine code generator converts intermediate code to machine code. Each intermediate code instruction may result in many machine instructions or vice versa. It is possible sometimes to compress many intermediate instructions into one machine instruction as well. It must also handle all aspects of machine architecture. For example, we must use the registers very efficiently, try to use as many registers as possible because registers are very fast. It must take care of the pipelining nature of the processor, then it must handle the cache sometimes, then if there are multiple function units, it must put them to efficient use. It should not be that only one of the function units is used and the rest are all idle, etc., etc. Generating efficient code is an NP complete problem. So, it is one of those problems which is extremely difficult. There are many techniques which are used to simplify this particular operation. For example, tree pattern matching based strategies are the best strategies. We will look at these in detail later, and this needs what is known as tree intermediate code instead of the quadruples and which we have seen so far. Storage allocation decisions are also made here. Register allocation and assignment are the most important problems here. So, which registers to use, which are the variables that can be placed in these registers, are they the best allocations that we can do, etc., are the questions we answer during this particular phase of compilation. Then we also have machine dependent optimizations. We saw machine independent optimizations a few minutes ago, and now we see some of the machine dependent optimizations. For example, there are what are known as peephole optimizations. So, these peephole optimizations they analyze a sequence of instructions in a small window which is called as a peephole, and using preset patterns replace them with more efficient sequence. So, it may be that a particular sequence of instructions is inefficient and there is a way of writing them in an efficient fashion which is known to all programmers. Such patterns can be put into a peephole optimizer. Redundant instruction elimination, here is an example. If you have a sequence load a comma r1 followed by store r1 comma a, then actually this is not necessary, it is not necessary to have this store instruction after all, because A already has the value that we require, and therefore, these two instructions may be replaced by load A comma R1 itself. The eliminate jump to jump instructions. So, there is a jump instruction which does not execute any other code, but just jumps to another jump instruction. Such multiple jumps can be eliminated. We will see a little bit of this later on. It is also possible to use machine instruction idioms, for example, use increment instead of load followed by add, etc., etc. So, instruction scheduling is a very important machine dependent optimization. It is used to eliminate pipeline interlocks and increase the parallelism in programs. It is nothing but reordering instructions in order to reduce the pipeline stalls. Trace scheduling is used to increase the size of basic blocks and then increase the parallelism. Finally, software pipelining is used to increase parallelism in loops. So, these are some of the examples of machine dependent optimizations that we have, and this brings us to the end of the overview of a compiler. So, now we begin the next lecture on runtime environments. Here is an outline of the lecture. So, let us see what runtime support is. Then we are going to see a few of the parameter passing methods. So, we will discuss storage allocation. What are known as activation records will be used throughout this lecture. So, we have to understand what they are. We discuss static scope and dynamic scope, what are these, why are they necessary, how to handle them, and so on. How to pass functions as parameters to other functions, then heap management, heap memory management, and garbage collection, one of the techniques which is possible to discuss in the limited time. So, what is runtime support? See, it is not enough if we generate machine code from intermediate code and then hope for the best. It does not run at all. Interfaces between the program and the computer system resources are also necessary. Otherwise, just dumping the code which is produced into memory and then trying to execute it will never work. There is a need to manage memory when a program is running. So, for example, this memory management must connect to the data objects of the program. So, it must understand how to fetch values of the variables, and then if there are parameters, how to pass them to functions, and then where to store the return address if there is a subroutine jump, and how to access the function result after the function returns, etc., etc., etc. So, programs normally request and for memory blocks, and then they go on releasing memory blocks whenever they are of not much use. So, all such memory functions must be taken care of by the memory manager. Other resources such as printers, file systems, etc., are also to be accessed, and the runtime support provides facilities to access these as well, but these are kind of outside the purview of our lecture. So, we are not going to discuss how to access printers and file systems, but we will stick to the other tasks that we mentioned, memory management and so on and so forth. So, these are some of the main tasks of a runtime support system. So, let us review the parameter passing methods. One of the most well known parameter passing method is the call by value method. At runtime, prior to the call, the parameter is evaluated and its actual value is placed in a location private to the called procedure. So, this is exactly what happens during call by value. Therefore, it is just not possible for us to change the actual parameters. We always operate on the copy. This type of parameter passing mechanism is found in C and C++. Of course, it is also found in Pascal, but Pascal is not used anymore. So, that is the reason I mentioned C and C++. C has only call by value method of passing parameters. It does not have other methods such as call by reference. We will see that those methods later. So, for example, even though we pass parameters frequently as to functions, passing pointers as parameters does not constitute call by reference. So, there is a generally misunderstanding that if we pass pointers, then it constitutes call by reference. It is not. I will show you an example why this is not possible in C. Pointers are also going to be copied. If we pass a parameter, a pointer as a parameter to a C function, the pointer is also going to be copied to another location, and then that copy is used. So, therefore, in C there is no way to write a function which inserts a node at the front of a linked list just after the header without using pointers to pointers, that is double pointers. So, we will see this in the picture here. So, here is the original linked list, right. We have written a function, let us say we assume that we have a function which is passed this header as a parameter, okay. This is a pointer to this linked list. So, when we make that function insert a node in the front of the header, what we want is something like this, right. So, this is the original header, then we have the new node which is inserted, and then the rest of the linked list. But because call by value copies this pointer to a private location, so this is actually a copy of the original pointer, the original header. So, the insert function actually inserts the node right here and then makes it point to this. So, we have not achieved this, but this is a completely different linked list. The original linked list is unchanged. This is not what we want. So, that is the reason I said you in C you cannot do something like this without using double pointers. Okay. So, that is about call by value, nothing more to it than this. Let us look at call by reference. At runtime, prior to the call, the parameter is evaluated, put in a temporary location if it is not a variable. Okay. So, the address of the variable is also passed to the called procedure. So, this is the difference. So, we have the address of the variable which corresponds to the parameter, and value is also available through this particular address. So, if the parameter itself is a function, there is not much that we can do. What I have said here happens, if it is the parameter is evaluated and put in a temporary location if it is not a variable, it is an expression. So, and of course, the address of this variable is passed, this temporary variable is passed, but it is not of much use. But if we had only one variable as a parameter, then the address of that variable itself is passed to the called procedure. Thus, the actual parameter may get changed due to changes to the parameter in the called procedure. Such a mechanism is found in C++ and Java, it is not found in C. The third method of passing parameters, we will look at an example after we finish call by value result, is called, the third method is called call by value result. This is a combination or hybrid of call by value and call by reference. So, what happens here is that the actual parameter is calculated by the calling procedure, it is copied to a local location of the called procedure. The actual parameter's value is not affected during execution of the procedure. So far, it is very similar to call by value. At return time, the value of the formal parameter is copied to the actual parameter if the actual parameter is a variable. So, if it is an expression, if the actual parameter is an expression, then you know there is not much that happens, because it would have been evaluated into a temporary, and this final value is also copied to the temporary. So, the original parameter does not change, but at this point it is different you know, if it is a single variable, it becomes very similar to call by reference. The original parameter which was passed now changes and gets the final value of the parameter you know that was assigned right now. But it is also different from the call by reference method. When global variables are passed as parameters to the call procedure, and the same global variables are also updated in another procedure invoked by the call procedure. I will give you an example of this, and this mechanism is found in Ada. So, here is an example to show how call by value result is different. A very simple program in Pascal style, and since we are assuming different types of parameter passing mechanisms, it is better to use different programming language construct to write down this rather than C or C++. So, there is a main program statement and a variable declaration A as integer. Inside this is a procedure which simply increments A, and there is another procedure R which carries a parameter x which is an integer, in which we have x equal to x plus 10, and then there is a call to the procedure Q and it ends. So, in the main program we initialize A to 1, call R with A, and finally print the value of A. So, let us see the result for various types of parameter passing mechanism as far as the procedure R is concerned. Let us take call by value first. So, we have A equal to 1 here, we called R with A. So, the value of A is copied to a local variable, that is, let us say this is x itself. So, x is incremented by 10, so it becomes 11, then Q is called. So, Q has you know it increments A, which is actually the global variable A and has nothing to do with x. X is a copy of A as far as R is concerned. So, A becomes 2, this is a global variable. So, when we print A, the value of 2 gets printed. Let us see what happens in call by reference. So, again A is 1, the address of A is passed to R. So, this x and this A are the same. Okay. So, when we increment x by 10, x actually has A itself has become 11. Okay. Even though it says x equal to x plus 1, in effect it is A equal to A plus 10. So, it has become 11, A has become 11. You call Q, A is further incremented by another 1, and therefore, A now becomes 12, and finally, when we print A, the value of 12 is printed out. So, this is call by reference. So, the original itself has changed. Let us look at call by value result. Again we have A equal to 1, call R with the parameter A. So, A is copied to the local variable x. So, x becomes x plus 10. So, that is 11, but so far we are within the procedure R, therefore, this x and this A are different, only the initial value has been copied to this x. Now, we call Q. So, Q actually you know increments the variable A. So, A becomes A plus 1, which is 2, A had 1 here and A became 2 here. This x was corresponding to the local variable itself, but then once R terminates, the value of x which corresponds to this parameter is now copied into the actual parameter, which is nothing but A. So, A now gets the value 11, which was the value of x. So, when we say print A, it actually prints 11. So, all these three methods of passing parameters actually yielded different results, because there was a global variable involved, and of course, the method of passing parameters itself is very different. Let us look at a very old parameter passing method, which is not very often used anymore in languages such as C and C++, but it is definitely used in functional programming languages. Call by name mechanism. This is in some sense a very weird parameter passing method, and let us see why. Use of a call by name parameter implies a textual substitution of the formal parameter name by the actual parameter. So, for example, you have a procedure R here. So, R has two parameters x and I which are integers. Let us assume that these are call by name parameters. Now, inside the procedure R, we assign I equal to 2, x equal to 5, I equal to 3, x equal to 1 and this procedure R is called by R with a parameter of b of j star 2 and j. The result of this would be effectively changing the body to this is I equal to 2. So, I corresponds to j here. So, textual substitution means j equal to 2, I has been replaced by j, and then x equal to 5, the textual substitution corresponds to b of j star 2 equal to 5, because x is nothing but b of j star 2. Now, j had the value 2, so this became b of 4 equal to 5. Now, j equal to 5. So, we had I equal to 3 here, right. So, this j sorry, this is j equal to 3, right. So, I equal to 3 here and therefore, we also have j equal to 3 here, this is not 5, and then we have x equal to 1. So, x is nothing but b of j star 2, this is the textual substitution. So, because j has picked up the value 3 from here, j star 2 now has the value 6. So, b of 6 gets the value 1. So, even though it is the same parameter b of j star 2, with call by name here we assign b of 4 equal to 5 and then here we have assigned b of 6 equal to 1. With call by reference parameter passing method, this would not have happened. We would have evaluated j star 2 once and then taken the address of b of j star 2 and passed that to this particular procedure. So, this x would have been the same location in the array B irrespective of what the value of j is. In call by name mechanism, it is not so, it is very different. The actual parameter corresponding to x changes whenever j changes. Hence, we cannot evaluate the address of the actual parameter just once and use it. That is what we would have done in call by value and call by reference. It must be recomputed every time we reference the formal parameter within the procedure. So, that is what I mean here. So, what really happens is we will have to evaluate that particular parameter again and again, right. So, a separate routine called thunk is used to evaluate the parameters whenever they are really used. So, for example, let us go one step before. So, yes. So, for example, here is x and this is I, right. So, b of j star 2 is evaluated again and again, okay, and the old value is not used anymore. So, it must be recomputed every time we reference the formal parameter within the procedure. So, this evaluation of the parameter again and again whenever we require it is done by a separate routine called thunk. So, thunk is actually a separate procedure. So, this procedure is to be generated by the compiler and it is called whenever the parameter is supposed to be accessed. So, the thunk evaluates the parameter and then the assignment to that parameter or the use of that parameter happens. So, this was found in the old language algol and it is still found in some of the functional programming languages. So, that is the reason we studied it here. Now, let us look at all the 4 parameter passing methods and see how they compare. So, here is a simple program called swap, which says temp equal to x, x equal to y equal to temp. So, this is well known to everybody. So, here we have y equal to 1 and then we have a I equal to 10. So, that means a of 1 equal to 10, that is what has happened, and a is an array of just 5 integers. Okay. So, then we have print of I comma ai, the routine swap is called with I comma ai, and again we print I of a comma 1, it is not a of I, it is a comma a of 1, that is what is being printed. So, let us see what happens during call by value. So, I is 1, so 1 is printed, a of 1 is also 10, so it is printed. Swap cannot be done in call by value, because only copies will get exchanged here, the originals will not get exchanged. So, 1 comma 10 is 1 printed again in the second print statement as well, because a 1 is still 10. Let us look at call by reference. So, print of I comma ai prints 1 comma 10, no problem so far. Then swap actually swaps these two values, right. So, I becomes 10 and a of I, which is a 1, becomes 1. So, what is printed here is 10 comma 1. When you look at value result, it is the same, it is just that the variables are copied back to locations. So, otherwise there is no difference between call by reference and call by value result in this particular program. It prints 110 and 10 comma 1. Call by name is different. First time it prints 1 comma 10, but then the second call after swap, the swap routine itself issues an error. Why? Let us look at the inside of the swap routine by textual substitution. So, temp equal to x becomes temp equal to I, because x is I, and x equal to y becomes I equal to a I. So, this now I equal to 10, since a I equal to 10, and now when we access a I is 10. So, we are accessing a of 10, which is an error, the array is supposed to be only 5 locations long. So, index out of bounds error is issued and the program terminates. So, this brings out hopefully the difference between different types of parameter passing mechanisms. So, now let us move on to code and data area in memory. Most programming languages distinguish between code and data. In other words, the runtime system will understand what is code and what is data. The compiler also understands what is code and what is data. Code is placed in some part of the memory, and within that code we never place any data, at least the compiler will not do it. So, code consists of only machine instructions and normally does not have any embedded data. So, the code area therefore does not grow or shrink in size as the execution progresses, right, because there is very little to change the code, there is no data, it cannot expand, it cannot shrink, nothing changes in between. But there are exceptions. For example, if you consider Java, okay, Java has this mechanism of loading classes dynamically whenever required. Classes contain basically the code for itself. Code, it contains a lot of code and it also has lots of data. So, this is an example where whatever I just said, code now the area does not normally shrink or grow in size is not valid. In Java, because of dynamic loading of classes, the code area can grow and it can also shrink. The class that class is abandoned once there is no use for it. There is something even deeper. Java has this reflection interface, and using that we can actually produce code through our programs and even execute that code through this reflection interface. So, in other words, not only have we have the feature of dynamically loading classes, we have the feature of producing classes which were never available anywhere, not to be seen at all, and then we can also execute this particular code. We can produce objects of that particular class, and then we can execute the methods of that class and so on and so forth. But we are not going to consider Java further in this particular lecture. So, we will assume that memory area can be allocated to code in a static manner, it does not change. But data area of a program may grow or shrink in size during execution. There are two types of allocations possible for memory. One is the static allocation, the other is dynamic allocation. So, during static allocation, the compiler makes the decision regarding a storage allocation by looking only at the program text. There is no execution of the code, there is no decision to be made at the time of program execution. Whereas, in dynamic allocation, storage allocation decisions are made only when the program is running. So, for example, there could be some stack allocation, names local to a procedure are allocated space on a stack. So, this happens in many languages, we will see this shortly. There may be heap allocation, for example, used for data that may live even after a procedure call returns, dynamic data structures such as symbol tables, and these require a memory manager, and sometimes they also require what is known as garbage collection, because if that dynamic data structure, say the symbol table, is not used anymore and the programmer does not do anything about it, the runtime system will have to run a program called garbage collector and reclaim this storage, otherwise we are going to run out of storage very soon. Static storage allocation, an example is here. Fortran 4 and Fortran 77 have this type of static data storage allocation. The compiler allocates space for all variables. See, Fortran has local variables, it has global variables. Okay. So, for all such variables of all procedures, the storage is allocated at compile time by the compiler itself. So, here is an example. There are main program variables, procedure P1 variables, procedure P2 variables, procedure P4 variables, etc., etc., etc. The code area of course is always static and it is in some other part of the memory. So, that I already mentioned. So, here there is no stack or heap allocation, there are no overheads which are actually related to stack and heap allocation. Variable access is very fast because addresses are known at compile time. There is no need to determine the address of a variable by adding various pointers and so on and so forth. And the pity is such a scheme cannot support recursion. The reason is recursion requires different locations for the same variable during its instantiation, whereas in static allocation this does not happen. So, what is dynamic storage allocation? Compiler allocates space only for global variables at compile time, these are in a static area, but space for variables of all procedures will be allocated at runtime. This is exactly what happens in C, C++, Java, Fortran 8 or Fortran 9. These are all languages where there is stack or heap allocation necessary for the variables. Variable access is slow compared to static allocation, since addresses are accessed through the stack heap pointer. We have to add something to that stack heap pointer, the offset of that variable, and then take the contents of that particular location and get the value of that variable. But the advantage with this scheme is that recursion can be implemented. So, since we are going to have different spaces for different instances of the same procedure, it is possible to implement recursion here. So, the unit of space allocation in dynamic storage allocation and in programming languages such as C, C++, Java, etc., is the activation record. So, we are going to use this information later on. So, let us understand the activation record structure. So, first of all let us look at the information that is stored. For each procedure it stores the return address, that is where should it go once this procedure is completed. It stores what are known as static and dynamic links. These are also called access and control links. So, these static and dynamic link is used to control the stack structure, and the static link is used for the access of global variables. Function result or the address of the function result is also stored on this activation record. Actual parameters which are passed to this particular procedure call are stored here. So, the caller will evaluate the parameters, and then depending on the type of parameter passing, either the value and or the address is placed in the actual parameter list. Local variables of the procedure find a place here. Then we require temporaries to evaluate large expressions and so on and so forth. So, those are all allocated space here. The machine status, for example, the caller would be using some registers, and before calling this particular procedure it would have saved its registers. But this procedure possibly calls some other procedure, and then it has to store its register contents in some place. So, saved machine status is the place where it stores the registers before calling the next procedure. Then there is space for local arrays. So, even though these local variables among themselves can host these arrays, we do not do that normally. We actually locate the array space at the end just for the sake of uniformity, and otherwise there is nothing very special. Please note that the order in which these have been placed here is not sacrosanct. It is possible that implementations choose different orders than what is indicated here. For example, function result could be at the top, and then below it could be the return result or the static dynamic link, etc., etc. So, with this we will close this lecture, and in the next lecture we will take up variable storage offset computation, which is one of the very important jobs that a compiler has to do. It has to find offsets for various variables, where exactly are they going to be placed inside the stack, etc., etc. Thank you.